sometimes there are people, I don't know if they have trouble with Zoom, but there's always a few people watching on YouTube. Okay, done. So, so thanks again to Chiara. Sometimes there are people, I don't know if they have trouble with Zoom, but there's always a few people watching on YouTube. Okay, there was some feedback there. So, okay, done. So thank you to Chiara for accepting an invitation in such a short notice. She will be talking about witnessing non-classicality beyond quantum theory. And okay, we can start. Okay, there was some feedback there.
Yeah, there was some echo and...
Thank you to Chiara for accepting an invitation. Yeah, sorry, that was my fault. We could listen to YouTube, which has a lag. So Chiara, yes, sorry for the technical issue. I think you can go now.
Okay. Yes, so thanks, Marius, for organizing this seminar series, which seems to be very successful. And also thanks to everyone else who has congregated virtually on this platform. And I have to say, I'm very excited to discuss this with you because, we were discussing just now that it's very nice to be able to present these ideas to a very broad community with different expertise. And so I'm looking forward to the comments that you will have. So I will start with something that we have been discussing quite a lot between us in various threads. And this is this idea to witness non-classicality or quantumness, but I prefer non-classicality because, as I'll discuss later, of course, this doesn't witness the full quantum range of features, but just a very specific feature of gravity using quantum probes. And so I reported here just to start the discussion, the main scheme that was proposed, where you have two quantum system, Q and Q primed, that interact with a mediator, which in this case is supposed to be gravity. And the idea is that if you can manage to get these two systems entangled just by using G as your channel, then you can say something about G's ability to be non-classical. And of course, there have been different versions of this argument, and somehow, so I reported the main ones over there. But today I would like to discuss something that is close to my interests, which is actually the angle that kind of led me to this kind of argument itself, which is how general is this argument that underlies the proposed witness of non-classicality. So granted that we can, let's say, make some argument that, when Q and Q prime get entangled through G, then G has got to have some non-classical degrees of freedom under some assumptions. How general can we make these assumptions? And I want to say why this is important. So this is kind of the core message of the talk. So if you get bored, you can just leave after this slide and you have got more or less what I want to say. The core message is that this prediction that, if you observe some degree of entanglement between Q and Q primed mediated by G, then G must be non-classical, is actually much more general than any specific dynamical model you can use to describe the coupling between gravity and a quantum mass. And in particular, it's based on these robust minimal principles of information theory, which are formulated in a way that's independent of dynamics, which is the key here. Why is it the key? It's the key because we are trying to probe a regime where there isn't, let's say, a consensus on which particular dynamical law we should be using. And so it seems very important that this conclusion that we reach, if we can observe entanglement between Q and Q prime in a putative experiment, is actually based on very general principles that are not specific to a particular model, to a particular dynamical model, for example, linear quantum gravity or another model. And I want to draw an analogy between this argument and Bell's theorem. So in quantum information, we know that from this theorem that if we manage to measure some correlations between two subsystems that exceed a certain value, we can immediately conclude that the theory that describes what's going on in the system cannot be a classical hidden variable theory. And this kind of theorem, Bell's theorem, is formulated in a very general language that only uses, the concept of certain statistical concepts, but not necessarily a specific dynamics. And this is actually what gives Bell's theorem its strength. And so I would like to argue that this argument, which underlies these witnesses of non-classicality in gravity, is actually of the same kind as Bell's theorem, if not more general. Okay, so that's the general message. And now I'll enter a digression, which is basically to introduce a set of conceptual tools and some principles that I think are the axioms on which you can base this general argument. And to do that, I have to talk about constructor theory. So I'll now open like a different section of the talk, and I'll go back to this after I've introduced some of the basics of this theory, that you can think of a proposed generalization of the quantum theory of computation in such a way that it is independent of the details of quantum theory itself. So first I want to motivate the theory. So why do we want to actually generalize quantum computing? So I've been in this field for a while, and it's a very successful field. So in a way you would say, well, why do you want to actually change something that is so successful? By the way, you could ask this about the theories that we're using in physics in general. So why are we looking for successors of those theories? And usually the reason is that there are some unsolved problems. And so I like to think of quantum computing as an unfinished revolution, in the sense that if you look at the theorems that you prove in quantum computing and the quantum theory of information, they are rooted, very deeply rooted in the formalism of quantum mechanics. So they do, they use these things like unitary evolutions and density operators and CP maps and so on. And all of these concepts are highly loaded with quantum theory itself. But now if you think that quantum theory might be modified, and of course, here there are several people who have thought of ways in which this might be done in order to, say, incorporate gravity or other phenomena, then you realize that if you are like me and you're kind of, you think that quantum computing is capturing a deeper structure, which should be robust against this change, then you think, you immediately reach the conclusion that you need a more general theory where you can still talk about things like entanglement, quantum superpositions, and the power of these things to perform computations, but without using the apparatus of quantum theory. And so that's one reason why you might want to generalize this quantum theory of computation. And then, of course, there's the other reason that's to do with the universality of computation. So, I mean, one of the nice underlying pillars of quantum computing is that there's a conjecture, which is kind of dating back to Turing and then was updated by Deutsch. The conjecture is that the nature allows for a computer that is universal in the sense that it can perform all computations that are physically allowed. And now this machine, in a way, could be considered as the most general machine that can be programmed to do whatever is allowed under the laws of physics. But actually, already von Neumann said that this is not the case. So that if you're interested in the theories of universal machines, the quantum theory of computation is not enough to describe that, because there's something that is even more universal than the universal quantum computer. And this is what von Neumann called the universal constructor. So to give you an example of something that a universal computer can't perform, you can think of the task of self-reproducing. So if you try to program your Turing machine to create an exact copy of itself, there isn't in this architecture of Turing machines space for this kind of instruction. Whereas, of course, there is in, let's say, a living cell. So a living cell can create a new instance of itself out of raw materials. A Turing's universal computer or its quantum version cannot. And yet, self-reproduction is a well-defined physical task. It can occur in nature. And the attempt by von Neumann to generalize the universal computer to the universal constructor was exactly to capture tasks of this kind. So the universal constructor, you can think of the ultimate generalization of the universal quantum computer. So it's a machine that can perform all tasks that are physically allowed, not just computations. And the theory of it should be something that goes beyond quantum information. So yet again, we have a reason to go beyond the theory we have. And finally, there is this other problem, which is, well, it's not really a problem, but it's more like a feature of our ways of describing or understanding or explaining the universe, which is that we use dynamical laws most of the times, but we also have other kinds of laws that are not formulated in terms of dynamics. So I just wrote here some of them, so you can see on the left the conservation of energy, which forbids a certain perpetual motion machine of a certain kind. Then, of course, the second law in its multiple forms. And then on the right, we have this nice conjecture, which I mentioned already earlier, the computability of nature, which says that a universal computer is possible. And the reason why there's a cartoon there is that I like to remind people about the fact that this was actually guessed by in the Victorian era by this person called Ada Lovelace, who was Byron's daughter, of all people. And she and Babbage worked on this thing called the analytical engine, which was like a prototype. I mean, actually, the ancestor of the universal computer. And had it been built, it would have been like the first universal machine, classical machine. It's just that they didn't manage because it ran out of funding. And so it's a very interesting story if you're interested. But let's say these principles, as you can see, they're not telling you that a certain dynamical law must be allowed, but they tell you that certain transformations are possible or impossible. And this might offer a key to go beyond quantum computing in the sense that I said earlier, because it tells us how it's possible to still make predictions and formulate general physical principles without committing to specific dynamical models.
Yeah.
So the question, yes.
Can you hear me?
Yes.
I don't know if you would accept interventions. There is a question by...
Yes, I do. I'd like to make this as interactive as possible. So if go ahead.
So feel free to unmute and ask a short question if you have one. Lee?
Yes, okay. I heard you use the word tasks, and that reminds us of functions. Are you proposing an extension of fundamental physics in which we're allowed to use functional vocabularies and functional explanations as we do in biology? Are we allowed to explain things in terms of what functions they perform?
Yes, perhaps. So function puts the emphasis. So the general answer is yes, but with a specification that is to clarification, which is that function puts the emphasis on the machine that performs the task. And I'm going to kind of, you're jumping ahead, and I think it's very interesting what you're asking, because what I'm going to describe in a moment is a theory that puts the emphasis on what tasks are possible. So what transformations are allowed or not allowed, never mind by, what is it that actually performs them. And if you think about it, actually, this is the spirit of these principles that we all know that I wrote here, at least if you consider them as formulated in some of their known formulations. For example, the second law has very many formulations, but there are some of those formulations where you really say, I don't really care about how you're constructing a perpetual motion machine of the second kind. It's just disallowed. It cannot be built. So it's not that a specific machine with a certain function isn't allowed. It's more like there is a task which can be performed to arbitrarily high accuracy. So the answer is yes, but with this, the warning that we are focusing more on the task rather than on the constructor. I'm jumping ahead as well, that performs the task. So I think function is a nice terminology within biology because they're interested in more in the things that perform the tasks. Whereas from the point of view of fundamental physics, the emphasis is more like on the tasks and whether they are possible or impossible. And I'll explain this probably in the next slide.
Good. One quick question now, and then I won't have to ask it later, and then I'll shut up.
Yes.
Is one of the tasks that can't be performed, that cannot be performed, enumerating all the tasks that a particular tool can carry out?
Well, I suppose this is a question for, whether or not this question has a positive or negative answer depends on the particular physics that you're thinking of.
I want to hear what you want to say. Go ahead.
Yes. So let me try to clarify this. So you have to think of this script. So what I'm describing here is not the particular set of laws that I'm going to discuss, but it's like the spirit of those laws and how they should work. So that's like the meta level of the talk. And then I'll kind of go closer to Earth later when we are kind of reconnecting with the original problem that I presented. But for the moment, I'm just describing the logic of these principles, and whether or not certain tasks are possible really depends on the particular laws of physics that you're looking at. So let me continue and just say that what I'm trying to say is that here, this idea that you can formulate laws not just as dynamical transformations, but as physical principles is useful, both for the first problem I mentioned, the one that interests all of us, the one to do with the generality of the weaknesses of non-classicality, because it frees ourselves from dynamics, but also for this more general purpose of generalizing the quantum theory of information. And possibly you can join all of these angles that I just presented. And this is what constructor theory is about. So let me get there step by step. So
can I ask a question just before you pass on to the next slide, please?
Yes, please. Yeah.
So regarding this question, what is possible to compute in nature, or
yes,
the third picture that you have, computability of nature, doesn't that depend on the details of the laws of physics that we have? And in particular, does it depend on our knowledge of the laws of physics? I'm asking in the context of the Gödel's incompleteness theorems, where you can never know all the laws of physics. So that's basically the application of Gödel. So in that sense, I mean, you can never be able to compute everything according to all laws of physics. So did you take into account these kind of effects
so let me just clarify.
How does that relate to?
Yes, this opens a very vast kind of field of discussions, but the sense in which I intend the computability of nature, yes, is rooted into a certain set of dynamical laws. And I'll just give you an example to perhaps kind of give an idea of what I mean. So in the quantum theory of information, we have as underlying laws all unitaries, so all possible transformations that satisfy unitarity. And we also have a very, if you like, unphysical assumption, some people question it, that is to do with the preparability of all states that are allowed by quantum theory. So under these assumptions, you can then say that a universal quantum computer, which is defined in a certain way, is allowed. And therefore, anything that under those laws you consider a computation can be performed by that machine. Now, this is a separate problem from what is true and what is it that you can prove to be true, which is what Gödel's theorem is about. And so in a way, I'm kind of agnostic about that issue. I'm just looking at a dynamical system where I can implement a certain number of proofs or computations separately. And then the computability of nature says that if you take the set of all such possible computations, there'll be a single machine that can be programmed to perform each one of them. And that's the universal computer. And whether or not one can exist is a question for physics. And I think this is a kind of topic of heated debate. And I, in a more prudential version of a talk that I gave somewhere else, there was a question mark under, after computability of nature, but this is why the question mark should be there. But for the time being, none of these will be relevant for what I'm actually going to say in regard to gravity. However, I thought I would give you like the kind of more general picture of where these principles come from and what is the logic behind them. So I gave 3 examples of things that more or less we all are familiar with. And if you have a problem with computability of nature, then replace that with locality or some other principle that seems familiar to you in existing physics. The point about these principles that I'm interested in is that they're not dependent on specific dynamical laws, although you can derive them, if you like, from certain dynamical laws. And why is that interesting is because they can act as guidelines for future theories. So that's the way I like to think of principles in a way. Okay, so if you decide to forget about dynamical laws and to take physical principles about what's possible and impossible as your basis, you need some fundamental elements still. And these elements are tasks. So tasks are, mathematically, you can think of them as sets of ordered pairs of input-output attributes, so which specify a general physical transformation. And these attributes will be defined in a certain space with a certain topology. And so there's a bunch of mathematical specifications of these things that you can attach to the attributes. But the important thing about these tasks is that to make a physical theory out of a theory of tasks, you need some constraints about what is permitted and what is not. And so we need to give a physical meaning to possible and impossible. And so the informal meaning in constructor theory is that a task is impossible if there is a law of physics that forbids it's being performed to an accuracy which is arbitrarily high, and it's possible otherwise. And before we go to the next remark, just let me give you an example. For example, the no-cloning theorem within quantum theory puts a fundamental limitation on copying certain sets of states, thereby implying that the copying task of these states, or these sets of states, is impossible. And why is that? Is because if 2 states are not orthogonal, we know that we cannot copy them perfectly. So there is a fundamental limitation beyond which we can't go as far as copying is concerned for those states. So impossible has to be understood in this way. And if there is no law that says that the task is impossible, then it's possible. And this means that it can be brought about with arbitrarily high accuracy by something. And here is how we hit this second point that I put there, which is the difference between a dynamically allowed transformations, which is what we are all accustomed with, something that is allowed by certain dynamical laws, and a possible task. So possible task, it's not just something that is allowed dynamically on an isolated system, but it's a transformation that can be brought about to this arbitrarily high accuracy by a part of the environment which has a specific property that is the property of performing the task and then retaining its ability to cause the task again. And this is an ultimate generalization of von Neumann's idea of a constructor. So a constructor is the part of the environment that, coupled to your system, can perform a certain task and crucially stays itself in its ability to cause it again. So it closes a cycle, and we can then abstract it away from the descriptions. And this is why we can only talk about possible and impossible tasks, forgetting about which particular constructor, if the task is possible, is performing the task itself.
Chiara,
yes.
Question. Is the system interacting with the rest of the world only through this sort of agents that performs the task and that makes it, or can it interact in other ways as well? That what?
No, it can. So it's a nice question. All there is that causes it, so everything that is necessary and sufficient to perform the task is within C. And C has this property of being an invariant, if you like, if you want to think of this dynamically. C is the part of the environment which is necessary and sufficient for the task to occur. And
but the rest of the world may, from the before the task to the after the task, the rest of the world might have changed necessarily. Yeah,
yes, it might, but the part that changes has to be specified within the input and the output attributes. So, and you may have side effects, in which case this will be a different task. So if you require the side effects to be constrained in certain ways, then you will have to put a constraint in these input and output attributes.
So it's not the entire world that has to be come back to itself.
It's not the world. There has to be one part of the world that comes back to itself.
But how do you characterize it? Well, what do you mean is the one that?
So let's say, okay, let's think of a concrete case. You have the task of cooling some fluid, some water, let's say. And so this task, you can think of doing it or actually heating it up. So heating it up is easier. So let's say you want to heat up some mass of water, some volume of water. This thing can be done by in many ways. And so for example, one way is the way that we know from thermodynamics. You can do this adiabatically in some very idealized conditions where you can just stir the glass of water that you have, and the water will heat up. And so if you like, you can think of the stirrer, the system of mechanical means that you use in order to perform the stirring task, as the constructor. And the energy that this system consumes as the mechanical energy as one of the subsets of the task, together with the mass of water, of course, which changes its thermodynamic attribute from lower temperature to a higher temperature. And so the task of heating up a mass of water with certain side effects, which you can represent by, let's say, a weight being lowered or raised in a gravitational field, is a possible task, because you can think of a mechanical machine that you can assemble that performs that task and stays itself unchanged in the ability of performing it again. Does that make sense?
Yes, but it's conditional to what you call the system, what you call the machine, and what you call the world, right? So it's
well, it's conditional to what you call your substrate. And then you have to look for, so first of all, you're thinking of it, this is gonna create a long digression, but
okay, so maybe I shut up.
No, this is important. I think it's nice to never mind. I mean, it's interesting to divert the flow. So I think you're thinking of it from the traditional conception of physics. So what you're thinking is, I have a dynamical law that says what the universe does. And here I have a subsystem, which I want to change from A to B. And then I am looking for another system in the rest of the universe, such that when initializing some appropriate state, when I couple it to my substrate, enables the transformation to occur on the substrate, and then stays itself in some invariant subspace, which is this C that I wrote here in a kind of pictorial way. So if you want to think of it this way, it's possible, it's just a model of what I'm saying, but what we are hoping is that we don't have to use dynamical laws to say what C is. Rather, we say there's a task which is possible, and this means that it can be performed to arbitrarily high accuracy by whatever environment you have. And that is actually your primitive statement. And then you derive other things out of this statement. Now, you may or may not agree that this is a viable thing, but I think I'm hoping that this makes sense, at least at the kind of logic level. So yes, the task depends on what substrate you define it on. That's the only thing you are focusing your attention on. And then whether or not a constructor is allowed is a matter for the laws of physics that you're using.
I have another question. Can you
Yes.
hear me? Yeah, in the example that you've given of heating the water,
Yes.
what would be the input attribute and the output attribute? What would it be?
So the input attribute is some mass of water at a given temperature, let's say a volume of water at a given temperature, and then some battery, which is in a certain state. You can think of this as a generalized battery with a certain energy. And then the output attributes are the volume of water at a higher temperature and the battery with an appropriate
these are so these are physical systems, these attributes. Yes. Because I was wondering why you were calling them attributes. To me, attributes is something like a property and not system.
Well, the systems don't change, right? So we are thinking of the substrate, the identity of the substrate is retained. So the water is a water, and in this.
Yeah, it's more like states. Like attribute is more like a state of a certain system.
Yes, attributes are sets of states. So if you want to think of, so I'm using attributes and not states because I want to think of a general set of the states that I consider as atomic or primitive in my theory. So I don't want to commit myself to tasks that only use one particular state at a time. I want to have like the possibility of considering the set of all states with a certain attribute, in this case, the temperature. Okay. This is a very, very, just borrowing, let's say, the conceptual structure of things like, well, various things like thermodynamics or if you like, theory of computation and so on. So it's nothing exotic, is just a more general sense of state than the microscopic state that we are accustomed to in kind of normal standard dynamical theories. Does this make sense?
Yeah, thank you. Yeah.
Cool. So this will be not so relevant for so in a way, I'm happy to discuss this a bit later, but maybe I just press on with because this kind of general discussion usually produces lots of interesting and nice reactions. But I think for the particular thing I want to say now, maybe we can, for the moment, just make do with whatever understanding you have of tasks and possible tasks, and then we can go back to it later if this happens to be problematic for what I say about witness. Is that okay?
Yeah, sounds good. Maybe let's leave you go to the end of your talk, and then the discussion is free. We can talk forever.
Great, that's nice. Sounds like a good plan. All right, so here's the constructor series program. As I basically already discussed it in a way. So you try to formulate laws of physics as principles that are scale independent about what tasks are possible and which are impossible. And by possible and impossible, I mean what I just said. And you don't assume specific dynamics to do so, and then you try to derive dynamics out of these constraints. And also, if the program works out, some constraints on the initial conditions or boundary conditions you can derive from these principles. Now, let me just stress that because constructor theory is supposed to have new principles additional to the ones you already know, it's not just a different language or a different framework in which you can cast dynamical laws where, sometimes I discuss with people who are studying resource theory and category theory on the other hand. And I think these two theories are can be thought of as frameworks, very general, very powerful, where you can express various different dynamical laws. And constructor theory is trying to work at the physics level in the sense that it's trying to add axioms or principles to the existing ones that we have in physics. So it may be expressible in category theory terms or in resource theory terms. And I think I've got some collaborators who are trying to do this. But I think we are talking at a different level here. And I think this is a program, and it may or may not work. And I think I found it very interesting when David discussed it with me when I was a student. And since then, I thought of using this approach that David proposed to tackle a more mundane problem, which is this one to do with stuff that happens in quantum information theory, where the quantum information framework doesn't quite suffice to solve certain problems. And so I guess here is where we go back to the problem I started with. So I'm very intrigued by this problem, which is called the problem of hybrid systems. So unfortunately, as it always happens, there are lots of different names around that mean different things, and hybrid systems has been used to mean lots of things. But the way I mean, the thing I mean when I say hybrid systems is just a system represented like this, where you have a system Q, which obeys a well-known dynamical law, for example, quantum theory, because that's what interests me, and another system M, which, well, either obeys the dynamical law in question, but its dynamics is really intractable, or it is something more exotic that may actually break the laws in question. In this case, of course, you can think of M as being gravity, which is what we were interested in at the start of the talk. And so, of course, you can take various approaches to approach this problem and make predictions about this entity, which is hybrid and doesn't quite obey a specific dynamical law. You can make some approximations within the existing dynamical laws, and these things are very successful. But there's also another approach, and this approach was followed a lot until a few decades ago. I think there are some examples in DeWitt and Feynman and Bondi, all of these people, and I think Carlo here also has been thinking about these things in a way from this direction, and many other people are connected right now. But then it has fallen out of maybe interest, in a sense that, at least in the field nearby mine, there is this other approach where you say, okay, I don't care actually about the specific dynamics, but I have some general principles that I know both Q and M obey. And now I want to make predictions just given these principles. And if someone is interested, there is this very beautiful derivation of qualitative redshift out of certain basic principles, one of which is the conservation of energy that Wheeler discusses, and I think dates back to Bondi and maybe even before that. That's an example of what I mean. The price you pay when you do this is that you might not be as quantitative as with a dynamical model, but the bonus you get is that your argument is very general and doesn't care about whether your dynamics actually is obeyed or not directly by any of these subsystems. All it cares about are these general principles being satisfied. So let's go back now to what we were discussing earlier. And now you recognize that this witnessing non-classicality of a system M using two quantum probes is just like a special case of this general problem that I outlined. And of course, you can think of M as being gravity, as most of you maybe have been thinking about, but other people have been interested in M being something like a macroscopic system, like a bacterium, whose dynamical evolution may collapse away from quantum theory or may just be intractable. And we want to know whether it behaves in some quantum mechanical way. Okay, so to tackle this problem in constructor theory, you can use a very general framework where you just use these two basic concepts of tasks and possible and impossible, which is the constructor theory of information, where you can talk about the constraints on a composite system, such as this one, where one part of it is quantum and the other part is classical, and or maybe not. And the reason why this is nice is that, unfortunately, with dynamics, these semi-classical systems or hybrid systems have been proven to have very many problems. I think Perez and Terno and other people have been discussing this a lot. And somehow with this principal approach, you can sidestep these problems. So the framework is general and is based on the concept of, on a few key concepts that I'll just discuss now. The first concept is an information medium. So an information medium is a physical system that has a set of attributes. which I call X here, which can be permuted and copied. So again, it's a medium defined by certain tasks being possible on it. And by copy, for those who are not maybe familiar with computer science kind of language, I really mean a reversible copy of this kind, where you have the first slot over here. I hope you can see my cursor, where there is a value to be copied, 0, 1, n, any of the values in X. And then there's a second system, which is like the blank target of this copy, where initially you start in a blank state, and then after the copy, you end up having the exact value that used to be on the first system. And we call X an information variable. And you can think of a very obvious example in quantum theory, which is the set of orthogonal quantum states. So once you define this class of information media, you can then construct a hierarchy of media where quantum systems are actually a very special case of these information media. So information media here are all the ones that satisfy these constraints I said. Superinformation media are a generalized version of quantum systems that again are specified just by requiring certain tasks to be impossible or possible in them. I won't go into details because it's not relevant for this talk. And the important thing is that in this framework, without using probabilities, without using specific dynamics such as quantum theories or others, you can actually talk about all of these different systems as being somehow special case of information media, which is quite nice because that means that you can treat nicely systems where you have quantum systems coupled with something else, which belongs either in the information media realm or in the superinformation media realm. And if you want to think of intuitively of what superinformation media are, just think of something that has most qualitative properties of quantum systems, but don't necessarily obey quantum theory. Then you formulate some principles about this information media. And the one that's important for us here is this thing called the interoperability principle. It's got a formal expression, which you can express in some kind of group theoretic language, but I prefer just to discuss here the informal meaning of it, which is that if you've got two systems that can have information variables and you consider them together, then the information variables of one can be copied on the other and vice versa. So it expresses elegantly and exactly this kind of property that we all take for granted about information, that it can be copied from any system that can embody it to any other. And now, armed with this stuff, we can then go back to the argument that we would like to formulate in very general terms and use this principle and another principle to make this argument as robust as it can get. So in this superinformation framework, you can define non-classicality in a more general way than you would otherwise do in any specific theory. And so you can say that the system is non-classical if it has one information variable Z, so a set of things that can be copied, and another disjoint variable X, which cannot be copied simultaneously to perfect accuracy together with Z. And of course, you can think of this property as being a generalization of the property of being non-commuting in quantum theory. And I call X and Z incompatible variable precisely for this reason. But it's nice because we are not using the kind of structure of quantum theory to say what that is. We're just specifying certain tasks that are possible or impossible. Then we assume two principles, and I'm kind of heading towards the conclusion of the talk. So the first principle is locality, and I'm hoping we will have a discussion about this later maybe. By locality, I really mean, so it's a slightly more general version of the no signaling property that, let's say, quantum information people are accustomed to. It's satisfied by quantum field theory and so on. And I'm happy to discuss the general expression of this maybe later in the discussion. And then the interoperability of information in the way that I expressed it earlier. So there are these two axioms, and then you can show by these two axioms, you can make a theorem which is dynamics independent. You can formulate a theorem which is dynamics independent, and then formulate an argument for this theorem that basically shows what I started this talk with. So the fact that if M, this mediator, is an information medium that can mediate entanglement locally between Q and Q primed, then M is non-classical in the sense that I said earlier. So it has these two non-compatible variables. And each of the terms in this sentence, including entanglement, actually can be expressed within the superinformation framework. So you can think of them as with the eyes of quantum theory or any other theory, but they are general. So they are more general than that, which is the thing that makes this, I think, exciting. So to summarize, this argument, which supports some of these witnesses have been proposed specifically when M is gravity, has a number of key traits, and they're all very appealing, I think. So the first is that, as I said, the argument is independent of dynamic and scale, and it relies only on these two assumptions or principles or axioms, however you want to call them. And the appealing thing about these axioms is that they're very general, and as far as we know, are obeyed by all existing theories that we consider as viable, including things like collapse models. I mean, there's a discussion to have about that, but then the second point is that this also allows you to say that if any amount of entanglement is observed on Q and Q primed, and M is the mediator, whether or not it complies to the particular predictions, quantitative predictions of a dynamical model, then you can rule out all classical models for the mediator that obey these principles, not just the decohered version of the quantum theory that you're using in order to describe the dynamics that couples Q, Q primed, and M. So in this case, I'm kind of thinking of these maybe linear quantum gravity models that we have used in order to make predictions about this regime. And this argument is trying to be more general than those particular arguments. And finally, it's nicely agnostic about the specific nature of the non-classical observables or variables. So if you happen to see entanglement and you have satisfied all of the various assumptions, we don't know really what that means as far as M is concerned, as far as what is quantum in M. So I like to think of these witnesses as, rather than as corroborating any specific dynamical model for quantum gravity, at least in this regime, as ruling out all classical descriptions of M in this context, which is, to me, sounds like a more general statement, and it has this nice, robust trait to it. And it's a bit like violating Bell inequalities, isn't it? Because when we violate Bell inequalities with some system, that doesn't necessarily mean that the thing that violates Bell inequalities is quantum. It just means that it cannot be described by certain local hidden variable models. So the test is actually agnostic about what dynamics we are treating. It's just a very crude, in a way, distinction, but very powerful, between stuff that can be described classically by hidden variable models and stuff that can't. And likewise, in this case, I like to think of this argument as a generalization of the logical Bell inequalities or Bell's theorem in the context of this hybrid system scenario, which goes beyond quantum information. And I think this is what excited both Vlatko and me when we started discussing this stuff. So to look ahead, I mean, I think there are lots of questions, some of which I am actually pursuing with some collaborators here that joined today, and also with some of my student collaborators. I'm not sure if they're around, but I think the first two questions are more for the audience that can, for the part of the audience that is has an expertise as far as this is concerned. So something I would like to explore with you. It would be nice. I mean, there's been a lot of discussion about what constitutes an observable in GR, and in more generally I think in quantum field theory, even as far as electromagnetism is concerned, there's a lot of discussion. But it would be nice to think of whether there's any bonus in thinking of information variables really as these copyable sets, which is a super general way of thinking about them, and it's maybe even more general than the stuff that's been so far considered to address the first question that I wrote there. And I don't know, it's a kind of leap in the dark. The second one is the question that I think we started discussing a bit with Marius and Carlo and Vlatko. What exactly are these incompatible variables in space-time geometry if you take a more appropriate description of gravity than the linearized quantum gravity model? And then the other two questions are to do with these other witnesses of non-classicality that have been proposed after the first two, which are explicitly rooted into the entanglement witness. So I'm referring, for example, to this witness that uses, for example, one single system and also others. So is there a way of making those witnesses as general as this? So is there a kind of underlying argument for those, which could be a consequence of this argument, or maybe an altogether different argument, but in the same terms, that could be used in order to derive those? And I don't know the answer, but I think we are kind of trying to think about that. And the last question is, it would be very nice, and I think constructor theory has it in it because we have a quantitative handle on things, to actually make this theorem a bit more quantitative in the form of linking the degree of incompatibility of observables in the sort of variables of information variables in the mediator to the degree of entanglement in the probes. And again, you can think of entanglement and as much as of the incompatibility of observables in this theory-independent way, which is actually the thing that makes this, to me, very exciting. And I think with this, I'll just stop, and I'll thank you for your attention. I'm very happy to take questions, more questions. Thanks. Thank you.
Yeah, thank you very much, Chiara. So, okay, we went a bit longer than usual, but there was a discussion in the middle, which is the point of these seminars. So I asked in the chat if any student has a question, would like to allow first students to talk. Don't be shy if somebody has something to ask. In the meantime, let me throw a very general quick question to Chiara.
Yes.
I have a more nasty one, but I will leave this later. Maybe it's going to fit in the discussion. Just to help also, just to give you the opportunity to tell us, how do you imagine the world, basically? So what ontology do you have in mind with this constructor theory in like?
Yes, I mean, I tried in the talk to decouple the specific. So I think, so because let me just make a more precise question. So in physics, like, let's say in quantum gravity, we imagine that what there is fields, including the gravitational field. It's the matter fields and the gravitational field. And that's what the world is made of. I think you have something else in mind. Is this true or not? Yes, I think those entities, if this picture makes sense, should be derivatives of the, so they could still be part of the ontology. It's just that by construction, the stuff that I consider as fundamental are these tasks and the statements about whether they're possible or impossible. And in a way, even states, ultimately, if this construction works, should be defined in terms of possible tasks rather than the other way around. But as you can see, this is a program. So in a way, I think I we don't have a constructive way to do that yet. But the purpose of the theory is to do that. And I think the early motivations for this were, as I said, I tried to say that there were a number of converging reasons. There are more. Possibly, for example, to also overcome certain problems that dynamical laws type of approach have, and that maybe are not so evident when you're trying to make predictions in a specific part of your lab. But when you're thinking exactly about what the description of the universe is, then for example, you start wondering about whether it's really true that you can explain everything there is and everything that is of interest in terms just of these statements about boundary conditions and dynamical transformations. And there are all sorts of discussions, but I think already information is a concept which is not quite, well, either it's kind of described as a kind of manner of discourse and not very fundamental in that picture, or it's not accommodated altogether. So in a way, the attempt would be to try to invert the logic of the explanation and get this part of the ontology, fields and dynamical transformations and so on, as like the consequence of these more fundamental statements about tasks. And I'm open to kind of a very, very heated debate on whether this makes any sense at all. But I think for the specific discussion we had, I find it very, very exciting that this stuff can somehow be applied in a way, irrespective of whether this program can work. I don't know if this answers your question.
May I come in with a question at this point?
Yes.
Yes, Chiara, I think it's extremely interesting you wanting to base a fundamental physical theory on tasks. But let me ask you some questions about tasks. Given, say, a particular object, say a screwdriver, can you iterate all of its tasks or enumerate all of its tasks, or is that impossible? Or given a task, can you enumerate all the physical realizations that might carry it out?
No, but that's the point. So somehow, when you say that energy is conserved, you are implicitly saying that certain transformations are allowed and others are not.
Yes.
And you don't have to say by what means these transformations are allowed. Likewise, when you say that a certain task is possible, you don't have to necessarily specify, in fact, that doesn't entail specifying all the possible ways, all the allowed ways of performing it. The content, the physical content of a principle of this kind is in the dichotomy between stuff that's possible and stuff that's impossible.
I understand, but when we have traditional physics, we believe we can enumerate the states, the particles, the forces. What I'm worried about, but also very excited about, and this relates to some work I'm doing that I could, with some friends, I could tell you about.
Yes.
Where we are functioning, where we are focusing on tasks and functions. And we're interested in the idea that these are not enumerable. That is, there is no space of possible tasks. There's no set of possible tasks. There are going to be tasks in 1,000 years that we don't know about now.
Right. In a way, you could say that it's also true that there are laws of physics, in whatever way you want to formulate them, that we are not aware of, but they're still out there and they're waiting to be discovered. So in a sense, the impossibility of enumerating all the tasks that are possible within a certain specific theory seems to me might also affect dynamical law type of approach. And it's more of a, so I'd be interested in knowing why in the specific study you're pursuing this thing pops up. But the kind of laws that we're thinking are, required to be expressed in terms of, possible and impossible tasks, in which case we are hoping to be able to capture the whole of physical reality with these statements. Whether or not this is possible is kind of an open question, and it's possible, it's conceivable that this may not work. But there will be a reason for why that is, and that will be interesting, I think.
What if I could prove to you that the number of possible tasks is vastly greater than the number of tasks that could be realized in the universe
I'd like to know what possible means in your language, because I'm not so sure we are using the same terminology.
However you enumerate the tasks that you were aware of, the number of tasks that may be expressed in the same language and the same formalism, I would call a possible task.
So you mean inconceivable task, let's say?
Let's say catalysts of chemical reactions. Do you think that that's a closed list or an open list?
Well, it could be open or closed depending on the particular physics you're describing.
In nature, I'm interested.
Well, we don't know the ultimate. I mean, the laws we have right now may be wrong. So the answer is I don't know.
Okay, let's discuss this.
But the question, so let's put it this way. Suppose your doubt, this problem that you're pointing out is out there, and it seems to me, and maybe I'm wrong, but let's say this issue that you're pointing out may be as much of a problem for standard physics, let's say for the standard dynamics that we have, as much as it is for whatever approach I was describing, because if you think you can think of possible tasks as being the things that are allowed through catalysts or constructors within the given dynamics. So the problem you're pointing out seems to me affects as badly the stuff that I'm describing as the maybe dynamical law approach. And
Sure.
This would be interesting to know where it comes from, because it sounds like an interesting thing. But I think a more tentative way of thinking about what I just described is, given all the problems that we already know about the current dynamical law approach, can we gain anything by switching to this other mode of description? And I think this is a less bold and less adventurous way of putting it, but let's say that's the pragmatic way I'm looking at this. So in a way, it could not work perfectly, but it could add more stuff. And I think this stuff we discussed today seems to me is a nice indication of that it can. And having said that, please, I'd like to know this stuff that you're studying, and it sounds like a very interesting thing.
Okay, thank you.
Thanks.
Okay, so
sorry, may I just add on to this discussion, just a short question, maybe for the rest of you, especially seniors who are more familiar with this thing. I want to ask Chiara also, are you familiar with the program of bootstrapping the S matrix in the quantum field theory, before the quantum field theory program was? So it is conceptually, it is the same thing. It is precisely the thing that you're describing. You basically start with a certain set of principles, and then you try to write down the scattering matrix for the elementary particle processes, which satisfies these principles, hoping to reach a unique prescription of what the scattering matrix should be. And this this was a program that existed during the 60s and before the standard model was formulated and so on. And this program basically failed. So
can I just say something? Maybe I wasn't. So this is a nice question. Thanks for asking it, because the aim of this program is not to single out a specific unique dynamical law. So we are not trying to derive one specific dynamical law out of principles. It's a different kind of thing. And I think that's also why it differs from various other attempts that have been made in the past to derive quantum theory out of principles. So, and the other thing is that we're trying to be more general, even in terms of the specific formalism that we are using. So we are trying to be, how can I say, so suppose before someone kind of came up with quantum theory, right? So people were a bit in the dark, and and we didn't know what to do with, we had Lagrangian and mechanics and Hamiltonian mechanics, and before that Newton's and so on. And let's say you were trying to guess what would come next, and you could be trying to do various things. And if you didn't have experiments to guide you, let's say, problems coming out of experimental evidence, you might be trying to vary, I don't know, Lagrangian mechanics, classical Lagrangian mechanics in some way. And well, it sounds very interesting that the quantum formalism is actually very, very different in some traits with respect to this classical initial formalism, even though it shares some kind of basic traits with it. And so the hope is that with these principles, we can capture, this principle can be robust against these kind of variations that can happen when you find a completely different paradigm for dynamics. And I think this is kind of motivated by quantum information theory, because it's a very interesting quirky thing that when you look at the quantum information stuff, where you forget about specific models to do with photons or spins or anything, you see a structure, an underlying structure, which is basically common, is in common between all of these things. And that's why you expect maybe that this is a structure that's a manifestation of a deeper symmetry, which we haven't quite grasped yet. And it is more robust than quantum theory itself. And it's the stuff that will still be retained with all of the entanglement, superposition, and so on, when we move to the next dynamical theory. So these principles should be robust against these changes, hence they can't single out a specific dynamical law. I don't know if this answers the question. Also, by the way, this is the speculative part of the program, because of course we haven't done this yet. And so, all of this may turn out to be just completely wrong. But it's nice to, I think, refreshing to look at things through that perspective, because it allows you to understand maybe even dynamics in a more, from a different angle, and this gives you a deeper perspective sometimes.
Okay, so Chiara, you are generating a lot of questions. There is there is somebody called Patrick Fraser, which here he put his video on.
Hi, can you hear me all right?
Yes, I can. Hi.
Awesome. Hello. Thanks for the awesome talk. It was very interesting. So when you were talking about basically treating the incompatibility of certain features in terms of their mutual copyability. So you've got two things, X and Z, copying one, not being able to copy the other, as kind of you mentioned that that's sort of a generalization of non-commutativity. And so the question that I have is, it's kind of related to what Lee was saying actually, about kind of the denumeration of the kinds of tasks that you can carry out. So when you're working with this universal computer, you're of course working in a setting where you're basically restricted by only being able to talk about finite things if you want things to halt. So if you want to actually copy the values of these kinds of properties, you have to be able to do so in a finite amount of time. So this is a rather imprecise question, sorry. But so there was recently this sort of big result resolving Cyrilson's problem. And my understanding of that result is that if we go to infinite dimensional quantum information, there are certain kinds of systems where their correlations can't actually be approximated by finite dimensional systems. So with that in mind, there's certain kinds of systems that are certain infinite dimensional systems where infinite dimensionality is really, really very crucial to their underlying structure. And in that kind of setting, you might not necessarily be able to approximate, well, you can't approximate correlations with finite dimensional systems. So then to be able to talk about the non-commutativity structure of those observables using this kind of universal computer setting, which is sort of necessarily rooted in the natural numbers, it seems like you might not be able to take that formalism and drive it all the way through to the full infinite dimensional setting. So my question is, how do you think about that kind of interplay, I guess?
Yes, it's a great question. I think the basic thing is that this is a proposed notion of information variable, and I think what one would say about such infinite dimensional systems is that those infinite dimensional things that you're using to describe your ontology are not the information variables that you use in order to test the theory. So, so although you can use, of course, by all means, stuff that is not discretized or finite dimensional to describe very many fundamental things, what this kind of theory I presented would suggest that it's only ever discretized also finite dimensional variables that you use, observables that you use in order to test the theory in question. And the way these infinite dimensional entities can be connected, as you said, is that you can think in some ways of these infinite dimensional things to be approximated to some accuracy or sometimes to infinite arbitrarily high accuracy by these discrete structures. And so so it seems to me that the stuff I was talking about tries to be as much as possible rooted into this idea that in order to test or let's say observe something, and in such a way that the thing that you're observing is error correctable, you do need discretized and bounded variables. And this is a statement about physics, which we can discuss about, and I think there are all sorts of views about it. But I think my angle on this is that the stuff that you were describing would be, it's possible for it to be a fundamental element of the theory, but then it's not within the things that that I would call observables.
Right. So you'd be referring to kind of coarse graining, like almost sort of the generalized probability theory type idea of like, here are the specific outcomes that exist on our measurement devices. Those are going to be, there's going to be finitely many of those, no matter what kind of experiment we carry out. Is that kind of the
That's right. Okay. So I think the information variables are not the fundamental things necessarily. In fact, they can be made of other things, which is why I was talking about attributes and so on. But the stuff that you can label as information within the context of a vast set of states or descriptors of your systems are only those things that you can copy in the sense that I said.
Right. Okay.
But that doesn't rule out the theory, a particular theory, if there are other objects that don't qualify as observables. It's just that they are not. I mean, I think in field theory we have examples of this kind where there are elements of the that we use to describe the field which are not observables, but yet they're part, the important part of the whole construction. And this is not. I don't think it's in contradiction with that. But thanks. This was a very nice question.
Awesome. Thanks, you. Thanks a lot.
Thanks.
So I think we can open a bit the discussion. I'm going to mention which are the people that want to ask you something. It's Andrea, and then Carlo, and then Pierre. So I'm going to leave you go each in turn and maybe also allow interventions by others.
Hi, Chiara. Thanks for your talk.
Hi. Sorry, I can't.
It was. I have two. Can you hear me? Sorry, maybe.
Yeah, I can hear you now. Yeah, sorry, there was a bit of a glitch.
Okay.
Yeah.
Okay. I have two questions for you. One is more like a yes or no question. This one is has anyone attempted a constructive view of constructor theory? So like saying what tasks are possible or impossible, and then they're driving the structure of quantum mechanics done, for example, in general probability theories or process theories and so on. And then the more open-ended question was, I was very intrigued by a statement you did quite quickly about how what is possible is impossible could affect statements about the boundary conditions of the universe. I don't know if you could elaborate on that.
Yes, so So I think some of my collaborators have been looking into trying to have certain models of what possible means given certain, certain sort of conditions on the states that you have in a certain theory, and given a particular dynamical transformation that's been postulated for the system in question. And I think this is this thing I mentioned earlier, where I was trying to understand how this framework I described can be phrased in resource theory, for example. However, I don't think there is a systematic study of this. In fact, this is part of the program to come. So the answer is maybe yes and no. So yes, we have some toy models. No, we haven't done any systematic study with specific laws of physics, other than, of course, quantum theory as expressed within the quantum information setting. And in fact, these kind of discussions we're having, make me hopeful that we might actually try to look into this specific question you suggested. The other thing about the boundary conditions, likewise, I think the reason why I mentioned that very briefly is that this is just a speculation, and I don't have any, so we haven't done any work on that. The only general argument I can say, it's not really an argument, but it's more like an intuition, is that so I think, although my knowledge of cosmology is very bad, the gist I get out of the idea of the theories about boundary conditions, or for kind of more mundane language, initial conditions, is that well, they have to be fixed in some way, and you can make various arguments for why they have to be one way rather than in another way. And these arguments may be questionable and controversial in many ways, and anyway, they are designed in such a way that the stuff we observe now is justified given these various kind of considerations about the boundary conditions. Possibly a way to solve this problem, the fact that you might find this a bit maybe not so satisfactory, or a bit arbitrary, or something like that, could be offered by switching to a different way of formulating the laws, because then your statements that are fundamental are really these things about if you take a substrate, which is a subsystem of the universe, and you say that a certain task has got to be possible on it, that of course places constraints on the kind of states you require to be there in the universe, and also the kind of dynamics that you allow. But it does it in a following a different logic from the usual stuff that we do. And this is why I just said in the speculative way that this could be helpful for this kind of problem. And also in a very crude setting, which is that of stellar automata, I think this was inspired a bit, but its comment was inspired by what these people in that are trying to model very crudely certain features of the universe with certain rules in stellar automata are doing. Is that there are two ways of going about modeling or trying to simulate certain features of the universe with such discrete systems. One is to say, okay, I've got a rule and I've got like a set of initial conditions, and now I want to see which rules are such that they, let's say, lead to certain asymptotic features of the dynamics of my system versus what happens with other rules. So there's one way of going about that problem, which is a bit similar to what we do in the when we approach the problem of initial conditions in the standard way. But you can also say, okay, I actually just look at a sub portion of my stellar automaton and I put some constraints on what tasks are allowed on that. And then I try to derive conditions that constrain the set of initial conditions for this simulator, as well as they can constrain the rules. And I think, at least in this setting, there are some groups who are noticing that there is a difference. Let's say there's at least a qualitative difference between what you can predict in what kind of conclusions you end up with in the first case versus in the second case. And this is not an argument, it's just to say that there is a kind of intuition that this logic may be useful. But both your questions are probing stuff that I haven't done yet, and about which I know also not so much. So I would be happy to be enlightened, if anything.
No, this was a very open question, but so why wouldn't you consider also final conditions and not just initial conditions?
Yes, I think so. Sorry, was that a question or?
So, yeah. It was a question, like, would you consider also that is possible and impossible?
Yes.
Not just initial conditions.
Yes, in fact, you could say that there is a bit of an arbitrariness as far as what is it you choose as your...
yeah, exactly.
Yeah, whereas if you talk about possible tasks, that's kind of implies conditions on all of these things. So in addition to, you get as a bonus the fact that you remove this arbitrariness, so to speak. So yeah, nice. That's actually another nice point to say that this might be a helpful thing to look at. Sorry, a helpful way of looking at this. Thanks.
Thanks.
So Chiara, there is Carlo, Pierre, Robert Deckel, and Liz Molin that have.
Chiara, I'm curious. Can you hear me?
Yes.
I'm curious to know how you would answer to two sort of obvious perplexities or objection that come from a more sort of physicist view on what you're saying, which is the following. I can view constructor theory in two ways. It's a very powerful set of conceptual tools for analyzing situations and for addressing specific questions, or another way, which is the one you're emphasizing, as a proposal for something very fundamental for addressing the description of nature. You say even replacing the idea of dynamical laws. Now, if you want to view this way, there are two things that come immediately to mind. One is that you're probably familiar with Einstein's distinction between principal theories and constructive theories. Now, constructor theory is not a constructive theory; it's a principal theory. To confuse language here, so maybe I shouldn't use Einstein language. It's a distinction that has been, had a lot of influence, and philosophers have constructed a lot about that. But Einstein's idea, and the recurring idea in philosophy, physics, and in physics, is that a principal theory, it's less fundamental, is not what you want. And Einstein insisted a lot, he being the magician of principal theories, of saying, once I have a principal theory, I haven't yet understood what's going on. I have a very great grasp on the story, but I don't know the story and I want to know more. And in fact, the quintessential principal theory, which resembles constructor theory, is thermodynamics. And thermodynamics is a prototypical thing that it's wonderful, it's powerful, it's fantastic, but then you sort of want to know what's behind it. And then you go to statistical mechanics or whatever, you open a discussion, and then you might argue that it's true within a domain and not outside the domain, and so on and so forth. So the first obvious objection or puzzlement is why do you want to go in a way which has been powerful, but never powerful as a fundamental approach to nature, always powerful as a tool. And the second question, which is for me is even more interesting, and maybe that's even more what I want to hear about you, in the spirit of what I just said, constructor theory and tasks smell dramatically of anthropocentrism. And in a sense, the strength of physics has been getting us away from anthropocentric notions as fundamentals, not because anthropocentric notions are wrong, but they're just because it regards us and our specific way of dealing with nature, and not nature by itself. So I would find, as Carlo, enormously interesting to understand how constructors come out from dynamical law, and much less interested, how the notion of tasks can be framed in an anthropocentric, in a non-anthropocentric but naturalistic view, in which I don't have tasks and objectives and separation of the world to start with, but somehow I start from a picture of nature and these things emerge. How would you respond to these two questions? I mean, the objection. The first being, principal theories are traditionally not fundamental. Powerful, but not fundamental. And the second being, Constructor, it sounds a lot as anthropocentrism, thinking in terms of complicates biological notions which are not in nature.
Yes, so the first point, I mean, there was this, I think Harvey Brown has this very cute way of talking about this, which is shortcut physics. I think, I mean, he likes to say that principles are, you know, just ways of going about physics when you run out of options with your dynamics and you're trying to make a shortcut, kind of a bit like with the second law, let's say. Now, I would like to point out that the fact that we feel like that, and this includes what I think Einstein thought, as far as I understand, is really an arbitrary assumption that we are taking, which is based on the fact that so far the dynamics approach has been very powerful, and it has explained most things that we found problematic. And it still does, and it's very, you know, very far-reaching and universal and so on. The reason why I think it's worth revisiting the principal approach after what, you know, this Einsteinian critique of it, or depending on how you think Einstein, I mean, I think also the said Harvey Brown has also thoughts about that in terms of what Einstein was thinking about his own theories and so on, but never mind. So the reason why I think it's nice to revisit this at this stage is that since then, this concept of, I mean, there are some concepts which we use in physics a lot, the chief one being information, but others too, like work and heat and things like that, which if you try to capture in the dynamics approach, you necessarily end up treating them as emergent. So you can have a theory of those things, but it's at best it's an approximative theory. So usually it involves approximations like coarse grainings or things like well, certain statistical mechanics techniques and stuff like that. And therefore the theories of those objects in this approach, in the dynamics approach, cannot really be fundamental. So these objects we are using a lot to describe things, and they, the information-theoretic structure of certain dynamical laws seems to be even deeper than the dynamical laws themselves, like in quantum theory and quantum information. And yet these objects are just approximative in this dynamical law approach. So it seems to me that this is enough of a reason to try to explore as an experiment what happens if you take the other statements as primitive and exact, and then you try to derive the dynamical laws as a consequence. And by the way, I think that so dynamical laws we're going now into the very philosophical discussion. So of course, from the pragmatic point of view of people who are doing physics, it's very, very important to have things that allow you to make predictions, and dynamical laws are great at that. But let's say, because you're going to the kind of philosophical discussion, dynamics cuts out all sorts of bits that are essential to describe physical situations. You know, the chief example is this one where I can look at what's going on in a particular computer, and then I can ask, why is this particular transistor off? And so the dynamical law approach would give you an answer, which is at best something like, oh, it's off because the initial conditions of the machine were such that that was on or off, depending on what the encoding was at the start. But there's another answer to that question. And the answer is, well, it's off because the factoring algorithm that you programmed in this machine had this number as an input, and the particular transistor you're pointing at is encoding the output. Now, these two levels of explanation are actually both necessary to know what's going on. And the one that I just said in terms of information is not quite captured by the description in terms of states and dynamics. And this is a very silly example, the one I gave. But I think there are more of these things in physics, in fundamental physics. And the hope that kind of drives this program is that, just like it happened with quantum theory and quantum information, switching to the mode where the principles are fundamental and then the dynamics is derived can teach you more about dynamics than you would otherwise, and about physical reality in general, than you would otherwise be able to grasp just by restricting yourself to this set of statements just in terms of dynamics and initial conditions. It's a very bold statement, and as I said, I find it very interesting. I take it with a lot of skepticism myself, but I think it's very intriguing that somehow, since Einstein's times, we have understood much better some of these concepts that would have been considered as emergent and derivative, like information. And it's very intriguing that they sound like they are actually fundamental elements in some realms of physics. And we can't regard them as such if we stick to the dynamics approach. And so this is an attempt to save those concepts and to make them as, make those the fundamental building blocks and the other things as derivatives. The other stuff that you said about anthropocentrism, I think or anthropomorphic, whatever, so I see the theory as doing the opposite. So I think there is
anthropocentric. Anthropomorphic means having the shape of a man. Anthropocentric means considering human central.
Yes. So these concepts are. So I think what the theory does is that it actually allows you to look at things like information in a much less, in a more objective, much less objective, and much less anthropocentric way. Why? Because so the constructor is not the basic element of the theory. It only is if you think of the theory as within the dynamical law approach, because as soon as you think of a task being performed, you have to think of what is performing it, and then you have an infinite regression that goes back to either the initial conditions or some other kind of base that you put for the recursion there. But tasks by themselves and the statement that they are possible or impossible are not anthropocentric at all. I mean, the statement that energy is conserved, which is about the fact that a certain task is impossible, can be stated whether or not in a particular universe that you consider where that principle is satisfied, there are humans or human-like entities. And likewise, the fact that something is copyable, right? So when I say an information medium is one that has, let's say, a certain set of copyable states, it seems to me that that is the quintessential way of talking about information in an objective way, because it doesn't use it doesn't appeal to there being an observer, a sentient being around, or stuff like that, which is actually one of the ways in which you can sometimes think of information. And that's also one of the reasons why people think that information cannot be fundamental at all. But if you think of it as really being about there being certain sets of allowed possible transformations, it seems to me that doesn't actually bring humans or human-related things center stage, but it allows you to free those concepts from the anthropocentric kind of fault. So in a way,
why do you call them tasks then instead of processes?
Because processes can be anything. A process is a very generic word, seems to me, whereas task really entails this idea of something occurring when the substrate in question is presented to some system, which doesn't have to be human related, but it's just part of the environment, that has this property that it stays unchanged once it's performed the task, in its ability to cause the transformation of the task again. I think also we call the task because it's a generalization of a computational task. And I understand that computational task brings in the idea of a computer and all of that, and that you don't like.
Yeah.
But that, okay, let's say I take the point about the terminology being perhaps misleading, but of course, one has to deal with whatever is given, in the sense that if you take process, then everyone will. So I think if I say process, people will just attach to it whatever meaning they have in their head, and this could range between something that is maybe close to what I mean and something that to something that's very far. Whereas the concept of task at least suggests that it must be something a bit different from a trajectory or a dynamical transformation. So I if you have a suggestion for a better terminology, I'd love to hear that. Also, because talking about ambiguities, there is this fact that construction, I mean, there are all sorts of other things that have constructor in them, and this generates all sorts of confusions. But never mind. I mean, that's how it is when you give names to things. But I don't think so. To sum up, I think it's nice to revisit this principle as shortcut physics usual take on things, and this is a challenge to that view, and if it works out, maybe it's a successful challenge, and if not, no. And then you just use it as a tool. And the other thing is that I don't think it's bringing in humans as central things in the fundamental laws of physics. That would be a bit it's anathema to anyone. But what it does is that it actually frees some concept which has been regarded as emergent, subjective, and so on, frees them from the human related stuff, and it puts them on objective terms to do with counterfactuals being there or not being there. I don't know if this answers your question.
Yeah, thank you. Very, 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 very interesting. Thank you very much.
So first, let me make the comment that at this point of the discussion, you can simply interject. Lee has been raising his hand for some time.
Pierre was waiting.
So I know, but
that's right.
You can combine, presumably you have an algebra of tasks where you can combine tasks.
Yes.
So let me ask you a specific question about that. If I have task A and task B, and the task A and task B, are there 3 possible tasks or 2? In other words, if I have the set of task A and task B, is that a 3rd possible task in addition to task A and task B?
Yes, so let's say if task A and task B are both possible, then it's one of the axioms of constructor theory that task A composed with B, and I can elaborate on what composition means, is also a possible task. So,
and is your composition associative or commutative or not?
Not commutative, but associative, yes.
Okay. Have you tried to count them?
Say it again, sorry.
Supposing I have a system, well, you're one of your universal constructors, and it has a set of tasks it can make.
Yes.
And suppose that you add to it a task which combines tasks. So constructs further tasks from the set of tasks that can be made initially. Have you tried to count how large that function after n iterations grows with n?
Well, this depends on the other axioms that you are taking in your theory, I suppose. And
well, it's very shocking how fast that function grows.
Yes, you're talking about the efficiency. So you're now thinking of, I think this is nice because it's probing this direction of the universal constructor, which is very much, I think this is very much of interest to David. And I think he would.
But I think I'm challenging it. If you ask how, if you're allowed to make a task that combines tasks and is non-commutative and distinguishes subsets of the set of tasks as distinct from those tasks, then if you try to count that, you'll discover that it's super exponential. it grows much faster than any exponential. And the task of iterating the possible tasks looks much harder than you might have expected at first. So let me give a concrete example.
Yes.
Is an invention, that is where a patent is filed, a task? Or is it a description? Would you count it? If I invent something and write a patent, am I describing a task?
Sorry, there was you broke up during the question. Do you mind repeating it? Sorry.
If I'm an inventor,
yes,
and I invent a new thing to do that didn't exist before, have I invented a task?
Well, I'm asking if I invent a machine that can suddenly detect something that has not been described so far by the current dynamical laws, have I invented new dynamical laws? I don't think so.
I will ask that question, but that's not the question that I asked.
Well, it's a similar question because the set of tasks that are possible or impossible and describe a certain physics should be given whether or not these tasks are actually performed in a specific instance of the universe that obeys those laws. And actually, this is the difference between a task being possible. Let's give a specific example, otherwise we're going to these very abstract things. So let's say, when I say that conservation of energy is satisfied in a certain system, that doesn't necessarily mean that a machine that can, say, transfer energy from A to B compliant to that law has to be built necessarily. So there is a difference between stating something as a possibility versus the fact of whether or not a specific constructor or machine that can perform the task in question will or will not be built. So these are two. I think we are. I understand what you're trying to. So I think if I understand correctly, your point is something like, if I have a set of possible tasks in the repertoire of a constructor, how do I? How does let's say the repertoire of this constructor change, given possible new ways of performing certain tasks that currently are not included in that repertoire? Is that correct?
I'm concerned with that because that happens in biology, and I'm concerned to integrate biology into physics.
Right. So so constructor theory is not concerned directly with that question because it just puts some fundamental limitations on what the repertoires of constructors can be. And how a specific object which approximates a constructor which exists out there in the wild evolves or becomes more and more complex and able to do more and more tasks is something that would be constrained by these principles, but is not necessarily it's not the level at which I'm stating the principles. So when I say that the task is possible, I really mean it as or impossible. It's just a fundamental limitation on what kind of such entities you can then have in a specific universe that obeys those laws. And so I fear that the discussion is somehow split in two levels. The one I'm talking at is to do with a general abstract fact of certain tasks being allowed or not, whereas what you were discussing has to do with what happens to specific instances of constructors for tasks once they are up and running and how they can evolve into each other. And I think I haven't looked into that question, so I wouldn't know how to answer it, but I don't think it's necessary it's not a necessary foundation for the laws I'm talking about. Possibly I'm misunderstanding the question.
Okay, well, thanks for now. I'll send you something.
Yes, it would be nice. I would like to know of any counterexample or something that creates, that makes these axioms problematic or something like that. That would be of interest to me. So please do.
Okay, thank you.
Thanks.
Okay, so I have a question. Can you hear me well?
Yes.
Okay. So my question is about the meaning of what's possible and what's impossible. Mm-hmm. Because in natural language, it's not completely clear what it means to be for something to be possible. In different contexts, it can mean different things. For instance, there are at least two meanings. For instance, I can say it is possible that I drink a cup of water. Mm-hmm. I know this, and that's true because I've done it before. But I could ask the question, is it possible that I can ride a unicorn? and if I can ride a unicorn or not? And this notion of possibility of impossibility, I think is not answered by physical laws, because I would need to know if there are unicorns or not to answer this question. And physical laws don't answer, maybe there are, maybe they are not. And so this example to say that in between what's possible in a physical theory and what's impossible, for sure, there may be many facts which fall somewhere in between, where maybe it is possible, maybe it's not, or there are kind of new different meanings of. It's not as clear as we may think at first thought. And I think to make the meaning of what's possible and impossible precise, we need some maybe more mathematical formalism. And that's done, for instance, there are many examples in mathematics where we do this kind of thing. For instance, when mathematicians define what's constructible and what's non-constructible as numbers, you have the constructible numbers and what they say is that they give very specific rules and a very specific mathematical formalisms that enables to say that each number is either constructible or unconstructible, and there is nothing in between.
Right.
And so this gap between what's possible and what's impossible physically, if you want to maybe to make it as small as possible, my feeling is that you need some very rigorous mathematical formalism. And so my question is, do you have such a mathematical formalism? Because I've seen in your presentation you have many principles that you're trying to implement, mm-hmm. But do you have some rigid structure that you can use, or how is it working?
Yes, so I think the question is very nice, and so first, this question that you just asked, the theory is phrased within set theory currently, and the proofs are constructing within this very, you could think of it as a very primitive mathematical structure, and I think any modern mathematical technique could greatly improve the proofs, and I'm very happy with knowing about such techniques and using them to make the proofs look nicer or even be more powerful or something like that. So just to answer your question as far as theory of uniform spaces, theory of topological spaces, all of these things are the things that I'm using when I perform proofs, and the same for my collaborators. But the question that you asked, I think I understand what. So the concept of possible has many different meanings, but the one that I defined is, I think, precise, and it really is a dichotomy between possible and impossible. So there are no things in between, and the reason is that. So the idea is that given a task, either there is a fundamental limitation to how well you can perform it, and this can be expressed in terms of epsilon and deltas as far as the accuracy of the task being performed is concerned. So either there is a limitation to these errors that must occur when you perform the task, or if there is no limitation, which means that you can think of an ever-improving sequence of objects that can perform the task to higher and higher accuracy with no bound, then we say the task is possible. And there are no things in between. And the sense in which we're talking about the unicorn, I think, is a different sense of possible. it's to do with well, either a unicorn occurring or not in the universe at some point, in correspondence to you being around as well and being able to kind of write it and so on. And I think it's a different sense of possibility. So I agree that in that case, there is maybe an ambiguity or an arbitrariness, but I think the sense in which I was discussing it, although I mean, I described it in a very informal way, so it possibly didn't kind of come through as well as I wanted, is this one where the dichotomy is really either possible or impossible, and there are no things in between. You just have to understand why that is. I think you have to think in terms of not what happens, but really in terms of these tasks that can or cannot be approximated to arbitrarily high accuracy. And I think that's matter for physics. And if you want to think of it in the dynamical law approach, really it's a matter for what the laws of the universe are and what the boundary conditions are, or what the states available in the universe really are. So you can express those two statements. The dichotomy between possible and impossible can be approximated with a model that's based on these concepts.
But so far, you say that with your mathematical developments, you have a meaning for what's possible and what's impossible inside general relativity, inside the quantum field theory, for all those physical theory that we already have?
No, inside quantum information theory, as I said. So I have a model for that in quantum information theory. It would be nice to have it in other theories too.
Okay.
But the general sense in which you can define this possible and impossible beside the specific dynamics is in terms of these errors that you can have when you perform a task, and whether there is a limitation to the accuracy to which you perform the task. And all of these concepts are defined in terms of, if you like, distances between states in a space. So they are somewhat more general than a specific model. And so the idea is that if you have a model for that in the more general way, then the other specific models in different theories should be able to accommodate those, should be able to implement that model, so long as they have spaces that conform to the assumptions that we have, which are, I think, in a sense, very general. So, spaces have to have topologies of certain kinds and various other things. But I think, so it would be nice actually to have a specific model in some of these theories that we are using, and they're very powerful and so on. And I think maybe this is kind of something we can do in the future.
Thank you.
Hey, I would like to ask a question. Can you hear me?
Yes.
Is that Robert?
So, yes.
Sorry. Yes. Okay. Just wanted to make sure it's you. You've been waiting patiently.
Yeah. Thanks. So, yeah. So let me first say I'm very sympathetic to this perspective that you are exposing here. And I think indeed it's a very promising approach, especially the sense of complementing this, the usual kind of dynamical law first perspective. To understand this a bit better, it has come up to some extent in previous questions already, the framework of general probabilistic theories in quantum foundations. And so you were talking about the superinformation framework,
yes,
using words like this. So maybe it would be good if you could explain a little bit more how these things are related. I mean, in general probabilistic theories, basically one also considers a whole range of theories that could be between classical and quantum, but a lot of things in between. And also there, basically, one abstracts from specific Hamiltonians or specific dynamical laws to a large extent. So there's provides a mean to talk about theories that are classical, quantum, or something in between. And of course, it's also more and more intertwined with the quantum information theoretic approach. So my first question would be if you could maybe be a bit more specific and in saying how this your approach relates to this general probabilistic theory approach. Now let me already ask a second question. So since you're taking this abstract and conceptual perspective, and you, so one of the purposes of this obviously is to get away from being dependent on specific dynamical law. And so what, from the, let's say, dynamical systems point of view, right? On the other hand, you still do retain an element of this, which is that you retain an external notion of time, right? So, well, at least in the way you have presented your notion of task, or especially in the example with the water that you're heating. So basically, there's a before and there's an after, and the task is a transformation that transforms something that's before to something that's after that. So my second question would be, do you think there's a way of generalizing this and trying to abstract the notion of task even from this primitive notion of time? So, okay, so I leave you with those two questions.
Nice questions. So the first one, I think the GPTs are in a way closely related to this thing I was describing. And I can say that hopefully what I described could be seen as somehow an underlying structure to some of the GPTs, because the theorems I described and the framework that I talked about doesn't rely on notions such as probabilities. So probabilities are not necessarily there. So you have in a way a much less well, actually, yeah. So I think you have fewer assumptions than, let's say, what you do in GPTs, because when you talk about possible and impossible and so on, you only have a kind of two possible values for probability, if you like, so if you want to think of it that way. And I think the theorems I described don't assume there being a probabilistic description of your states or measurements and so on. So you can then construct a probabilistic structure within constructor theory like things. And I think some of my work on this constructor theory of probability was based on finding some sufficient conditions under which you can define a probabilistic structure. And so, answering to your question, I think the GPTs could be a special case of these superinformation theories once you add on top a probabilistic description of your states. And I think this is something I've been discussing with a number of people who work in Oxford here on these topics. And I think it might happen in the future that we'll have a model of some of the superinformation features within GPTs. And the other thing is that in GPTs, the measurements are taken as somewhat primitive interactions, whereas in constructor theory, because we want really to have a handle on describing observables as opposed to other things that may not be observables, and they may just be things that are there for, in your theory, but they can be used to, to encode information. We need to be a bit more general than that. So again, I think in a sense you could derive some notions such as the observables that you have in GPTs out of these more primitive things that we describe in the superinformation framework. And I think this would be a very nice topic for future research in a sense. And I've always been hoping that this could be done. So the other question, which is a very deep question, the one about time, it's absolutely true. And I really like your point. So it's very nice, the distinction that you say about before and after versus the notion of time that you have in dynamics. So this is a more crude notion of time, if you like, but it's still a notion of time. And I think currently I don't have a solution to that, in the sense that if the constructor theory program works, then the hope would be to derive things like dynamics and time out of these principles that we have, which would be really timeless. And this is something that also David Deutsch has been kind of thinking about for a while. And I think it's necessary for the constructor theory program to work for this to be possible. And this could work along the lines of what some relational approaches to time currently existing in various dynamical approaches. But the precise steps in how to do it are part of something that I would like to do in the future.
Okay, thanks very much.
Yeah, thanks for the question.
Can I follow up on this if there is anybody else? Yeah, so the nasty question I had in the beginning is related to what Robert is asking.
Mm-hmm.
So I am assuming, I'm not sure actually if you want to do that, but I'm assuming you would want to go to a description of nature using constructor theory, where you have a notion of background independence. So in a sense, you don't have to assume some sort of space-time geometry. You want to see this thing coming out of it.
Mm-hmm.
One of the, I don't remember how you called it like a principle. You had two things. You said that it's very important, the notion of locality.
Yes.
So what is locality in constructor theory if I don't have space-time yet?
So you define it in terms of substrates. So you say that, so if you have, let's say, a composite substrate where you have, let's say, substrate A and substrate B, and there is a task being performed on substrate B only, then A shouldn't change. And if you like, this implies various ways of talking about no signaling that we have in, irrespective of whether you think of signaling as a particular dynamical process. So I'm kind of, it's a bit of more of an information-theoretic notion of locality.
So Chiara,
the one that you have in, the one that you have in field theory, for example. But it implies it, I would say.
I'm trying to grasp the picture you have in your mind. So when you say task, I guess the answer to for whom is for this universal computer, whatever that is, and that is somehow nature, maybe.
Yes, ultimately you can think of it like that if you want, yes.
And substrates, when you say substrates, you mean things that you feed in?
Think of them as subsystems. Subsystems, it's there are some differences, but they're not important for this part of the discussion.
Subsystems of what?
Say again?
Subsystems of what? So there is...
of the universe. So there's a universe and there are... This is actually... I mean, we can forget about constructor theory for the time being, and this notion of locality, I think, is the one that, let's say, is largely used in quantum information theory and in various other parts of physics. So like you've got universe, and then you have a theory that tells you how you can partition it into subsystems, and then you have descriptors for each subsystem, and then you want them to satisfy certain properties which make the theory local or not local depending on how things go. I don't know if this makes sense.
I don't know how to think about it more. I mean, I'm not very familiar with constructor theory. So maybe I'm asking very naive questions. What I'm trying to understand is how it seems to me that you're seeing this universal computer, whatever it is, as being outside of the universe, as being some property. And I don't understand how is this different than saying there are some dynamics.
Sorry, Marius, I didn't catch
I don't understand how this is different than saying that there are some dynamics. It seems to me you're saying there is a universe is made of subsystems, and there are things that can happen with to given subsystems, which are the tasks. What does that is something called the universal computer. But is this also part of the universe, or is this what we understand as the dynamics of the theory?
Okay, so let me just step back a bit. The universal computer or constructor, these are two different things. They may or may not exist in a specific physics. So that's, I think that was part, let's say, of the motivation why we are looking for extending the quantum theory of computation. So it's a separate point, I would say. But so you could have a physics where there are no universal computers and no universal constructors, but there are still tasks, and it's still possible to say that some of these tasks are possible and some other tasks are not possible, which is the kind of more fundamental set of statements. And when you formulate your possible, impossible task statements, you need to have a notion of what the task is being performed on. And this usually is a subpart of the universe. So it should be a subsystem of the universe as defined by a specific theory that you're considering. And then you can, once you have a partition of the universe into subsystems, you can then think of states that describe these subsystems. And then you can consider whether or not the theory in question satisfies or not locality. And locality, you have to phrase it, express it in terms of what is possible to do on a given system, given that you are, let's say, if you're performing a possible task on a different subsystem. And I think this is not a very specific thing to constructor theory. It's a notion of locality which underlies various things. So I think you're right that you can think of it without thinking of constructor theory at all. You can just I don't know, you can just take quantum theory and then think of locality in that context, and that would be okay. But I was drawing a distinction between this locality that I'm talking about, which is satisfied by quantum theory, quantum field theory, and relativity as well, and the concept of no signaling, which is a bit of a more specific notion that has to do with what you can do to observable features of a subsystem by performing transformations on other subsystems. And this is an important distinction because in quantum theory, there are entangled states, and sometimes changes that you could do somewhere else may not show up locally because locally your system is entangled with something else. And even though the overall state has changed, your local system hasn't changed. So I think this is kind of, but I fear that I think your question was a bit more general, right? So you were trying to dig a bit more into this notion of locality and say that you cannot formulate it without dynamics. Is that where you were?
Well, to be honest, where I'm confused is that I don't. You were trying to drive through the point that there is something fundamentally different than considering dynamics by thinking of principles, and I don't feel that I get it. Basically.
Okay, let's take this example with the conservation of energy, which is maybe something that we are all familiar with. And it's also uncomplicated because it doesn't involve statistical mechanics approximation to some degree, because you have a theory where you define energy. That might be a thorny problem, but let's forget for that for a moment. So let's say you have a theory where energy is well defined, and then you have a principle that says that it is impossible to change the energy of a substrate. That statement is not the same statement as what you would be able to prove, let's say, by showing that a specific dynamical law conserves a certain quantity. It's a more general statement because
why is it more general? This is what I don't understand.
It's more general because you don't need to have a dynamical law for that to be stated. So you can just say, whatever theory I have, whatever dynamics I have, so long as the theory has the notion of energy, my principle is that that quantity cannot be changed by isolated systems. I mean, of course, in isolated systems, of course, then you can kind of expand on that statement. But let's say the statement of conservation of energy you can think of it in two ways. You can think of it as a consequence, as something that you can prove specifically given a certain dynamical law, which is fine. That's a perfectly allowed way of thinking about it. But what I'm trying to draw at is that when you say the principle of conservation of energy, you can indicate a more general statement, which is supposed to underlie all of these various dynamics that satisfy the principle. But it's more general than those because it talks about those laws as well as possibly other ones that we don't know of. It's just formulated.
Okay, but I'm missing. I see, but I'm missing the goal. So this is where I'm confused. One way to say what you're saying, I think, is that you're saying, okay, this principle constrains the possible dynamics, but I don't need a specific dynamics to say that energy is conserved. I'm just saying energy is conserved.
Yes.
And then, okay, you can add more principles, sure. But do you want to find the right dynamics in the end, or do you, I got the feeling that maybe
but the idea is that if you put together enough of these statements. Sorry.
Is there something like, I mean, let me put it this way, putting principles and then searching for the dynamics that satisfy them is pretty much what has been going on in physics since a long time.
Yes, but the principles were not those based on information, for example, because we don't have a way of formulating principles about information other than in approximate ways that are not quite satisfactory, let's say. So yes, there are some principles that we've been using for a long time, but hopefully these new principles should, by using the same logic, supplement the current ones that we have. And the goal would be to have those as your, at any one time, as your fundamental statements, and then get the dynamics as a sort of an emergent picture out of those. As I said, this is a goal. It's not, I'm not claiming that what I presented today hints that is actually a possible thing.
This is clear, is to understand the goal. So the game is the same.
Then, yeah.
The game is the same. It's just that you want principles that come from information theory.
And other things as well. But let's say the ones that I'm particularly interested in are those about information, yes. But that should be formulated in more general ways than those that we currently have in Shannon's theory or in, say, quantum information and so on, because those have dynamics in them, really. Or they are formulated with statistical methods that are not exact and so on. I think the point about locality is important, and I think it's interesting for the particular experiment that we've been discussing. And I think, I mean, this gravity, non-classicality in gravity witnesses, I think maybe we can have a separate discussion about it because.
Yeah, I don't know if there's people that still want to have a chat, and I don't know how tired you are because it's been 2 hours and 15 minutes.
I might have to, I have like an appointment in a little while. So
maybe we could wrap up at this point. We've held Chiara quite a long time.
Yes, if anyone has questions, please do send emails. I'd love to respond to them, even if now we can't continue with this. So.
Okay, so Chiara, thank you very, very much. Yeah, that was pretty exciting.
Thanks.
And,
thank you for the questions. And, yeah, thank you. Thanks a lot. Yeah, I look forward to the next one.
See you soon.
Take care, everyone. Yeah, thank you very much.
Bye-bye.
Bye.
Sorry.
Bye.
Hi. Sorry.
Yes?
Okay, don't worry. No. I had a short question, but don't worry, it's not.
Who is that? Emanuele.
Yes, yeah, I have another account, so okay, don't worry.
You waited until the very last minute. Send Chiara an email.
Yeah, but it's not so important. I guess I can find the answer in her paper. So I was not clear for me how is defined entanglement without Hilbert space and quantum. I don't know, some theory behind. If it was like non-local, or if entanglement is a system that are non-local, or I don't know, some other definition.
Actually, I was gonna ask a related question. I write an email, or you can write an email and CC me in it, because I wanted to ask.
Okay, I can write it.
Can I answer? Can I answer that?
Great.
Entanglement doesn't need Hilbert space, doesn't need anything. It's just violation of the Bell inequalities.
So it's not locality because some entangled state doesn't violate no Bell inequality. It's not the same thing.
I think that's what she means, right? She means that it's just something just defined in terms of probabilities in some appropriate sense.
Yeah, I don't know because I didn't understand because she was saying that he defined without using probability also the locality.
Oh.
Yeah,
but
I think
what I understood, but I never read some complete paper by about construction theory. So I just want to say I want to know if